Imagine this: a massive interstellar object traveling at an unimaginable 60 kilometers per second suddenly disrupts everything we thought we knew about the solar system. 3I, Atlas, the third ever interstellar visitor, is defying the laws of physics right before our eyes. Its orbit shifts in ways gravity and gas jets can't explain, challenging centuries of scientific understanding. This isn't just another cosmic anomaly, it's a crisis, a mystery so profound that it leaves us questioning the very rules that govern the universe. What's really happening out there? And what does it mean for the future of astronomy? This is not the first time such an anomaly has been observed. In fact, the behavior of 3I Atlas echoes what scientists saw in 2017 when a small interstellar object named Oumuamua made its way through our solar system. Much like 3I Atlas, Oumuamua's trajectory was not entirely consistent with the laws of physics as we understand them. However, unlike Oumuamua, 3I Atlas is much larger, making the scale of the mystery even more profound. While many astronomers were initially hopeful that the same explanations that worked for smaller objects would apply here, 3I Atlas has proven that we still have much to learn about these interstellar travelers. The first signs of 3I Atlas's unusual movement came on July 1, 2025. Astronomers at the Atlas Survey, which is part of a global network dedicated to tracking and studying objects in our solar system, spotted the object traveling at an astonishing speed of nearly 60 kilometers per second. This is fast enough to escape the sun's gravitational pull altogether, meaning 3I Atlas is on a one-way journey out of our solar system, never to return. That alone would have made it noteworthy, but the speed wasn't the only thing that made it stand out. The size of 3I Atlas was another factor that set it apart. Early estimates put its diameter somewhere between 3 and 7 meters, making it the largest interstellar object humanity has ever tracked. To put this into perspective, let's look at Halley's Comet, one of the most famous comets in our solar system. Halley's Comet has a diameter of about 7 kilometers, which is large by comet standards, but it is still far smaller than 3I Atlas. This new visitor was much larger than typical comets, and that raised immediate questions among scientists. The size of the object made it even more challenging to explain the shifts in its orbit. The usual factors that influence comet motion, gravity, solar radiation, and gas jets, didn't seem to be enough to account for the deviation in its path. As observatories around the world scrambled to track 3I Atlas, the data continued to pour in, confirming that its trajectory was not just hyperbolic, but practically a straight line through the solar system. Hyperbolic orbits are common for objects coming from outside our solar system, as they don't have enough velocity to be captured by the sun's gravity. However, 3I Atlas's orbit was unlike anything we've seen before. Its eccentricity, a measure of how elongated the orbit is, was calculated to be greater than 6. A figure that immediately caught the attention of astronomers. An eccentricity of this magnitude is rare, and what made it even more unusual was the fact that the path was so nearly a straight line, something that had never been observed in an interstellar object. But it wasn't just the unusual orbit that raised eyebrows. As 3I Atlas continued on its journey, scientists began to notice something even more troubling. The object's orbit was starting to shift. At first, this was subtle, not something you would notice with the naked eye. However, when the data was analyzed more closely by astronomers using the world's most advanced instruments, they realized that the object's path was deviating just enough to cause concern. The usual explanations, the influence of gravity, solar radiation pressure, or even outgassing from the comet, couldn't fully account for the observed shift. This was not just an interesting anomaly. It was a fundamental challenge to everything astronomers had come to understand about how objects move through our solar system. At this point, the situation grew more serious. Theories and models that had worked for centuries in explaining the movement of comets, asteroids, and other objects were being put to the test, and the results were concerning. Despite decades of advancements in astrophysics and the development of highly sophisticated tools to track and model the motion of objects in our solar system, astronomers were now facing a situation where the basic assumptions they'd relied on didn't seem to apply. Something was happening with 3I Atlas that couldn't be explained by the forces we've come to understand as fundamental to our solar system. This posed a bigger question. If an object as large, fast, and unique as 3I Atlas could defy the known laws of orbital motion in such a way, what else might be lurking out there that could challenge our understanding of the cosmos? What if there are other objects too far away or too small to detect that are moving in ways we don't yet comprehend? For astronomers, this was a crisis, and not just because 3I's Atlas was behaving in an unexpected way. It was a crisis because it exposed the limits of our knowledge. If the models and equations we've relied on for so long are not capable of fully explaining the motion of objects like 3I Atlas, then what else are we missing? The stakes were not just theoretical, they were about the very way we understand the universe around us. This was not just a curiosity, it was a problem. The standard rulebook that scientists have used to predict the behavior of objects in our solar system no longer seemed to apply to 3I Atlas. And as data continued to arrive, it became increasingly clear that this was a challenge that could not be ignored. What we are witnessing now is not just the arrival of a new interstellar object. It is a moment in time that could redefine everything we thought we knew about how cosmic objects move and behave. The question now is, what is the true force at work here? And what does it mean for the future of astronomy? This marks the beginning of a new era in our understanding of the cosmos. The investigation into 3I Atlas has raised more questions than answers, and the answers that do come may not fit within the conventional frameworks we've relied on until now. This is a critical moment for astronomers, as they look for a force that is not immediately obvious, one that could shake up everything we thought we knew about the universe. And as we continue to observe this object and others like it, it's clear that the story of 3I Atlas is just beginning, and the conclusions drawn from this mystery could change the way we view the entire cosmos. On July 1st, 2025, astronomers at the Atlas Survey made a startling discovery: an interstellar object moving through our solar system at a mind-boggling speed of nearly 60 kilometers per second. This object, later confirmed as 3I Atlas, was not just another asteroid or comet, it was an interstellar visitor, something that came from beyond our solar system. The discovery was remarkable for several reasons, but what really caught the attention of scientists was the sheer speed of the object. At this velocity, 3I Atlas had the necessary energy to escape the sun's gravitational pull forever. In essence, it was on a one-way trip, never to return. What made 3I Atlas even more extraordinary was its size. Estimates of its diameter ranged from 3 to 7 meters, which, although small in cosmic terms, made it the largest interstellar object that humanity had ever tracked. For comparison, Halley's Comet, one of the most famous comets in our solar system, has a diameter of about 7 kilometers. But even Halley's Comet, which is considered a giant by comet standards, pales in comparison to 3I Atlas. To put it simply, 3I Atlas was big, and it was moving fast. Given its speed and size, astronomers around the world were quick to turn their attention to this strange object. As they studied it more closely, they began to realize just how unusual it truly was. While it was moving at an incredibly high velocity, which is typical for interstellar objects passing through our solar system, the object's orbit was what truly stood out. The object's orbit wasn't just hyperbolic. It was more than just a curved path. Its orbit had an eccentricity greater than 6, a value that made astronomers take a step back. An eccentricity this high was practically unheard of, and the implications were profound. It meant that the object's path wasn't just highly elliptical, it was almost a straight line. At this point, it became clear to scientists that 3I Atlas wasn't following the rules that govern the motion of most objects in the solar system. Its path through the solar system was far more direct than anything previously observed. In fact, its trajectory looked almost like a straight line, which is an anomaly in itself. Typically, objects entering our solar system from interstellar space follow highly elliptical orbits, and their paths are influenced by the sun's gravity and other factors. But 3I Atlas appeared to be taking a shortcut, almost as if it was skipping over the usual gravitational influences of our sun. As the days went by and astronomers continued to track the object, it became clear that 3I Atlas was something special. Its trajectory wasn't just unusual, it was unprecedented. The object's high speed, its size, and the way it was moving through the solar system were all factors that seemed to scream out that this was not a typical cosmic object. But what made 3I Atlas particularly intriguing was the fact that its orbit was not as predictable as astronomers had hoped. It began to veer off course. Now, this wasn't a dramatic deviation, nothing that would be immediately noticeable to the naked eye. But it was enough to set off alarm bells among the world's top orbital modelers. At first, the shift in the object's trajectory seemed small, almost insignificant. But as more data was collected, the deviation became more pronounced, and it was clear that something was not right. The object was not following the path that scientists had predicted for it. It wasn't behaving as expected. And the more astronomers studied it, the more they realized that the usual explanations for such movements weren't enough to account for what was happening. The typical forces that influence the movement of a comet or asteroid, gravity, solar radiation, and even outgassing, didn't seem to be fully explaining the shifts in 3I Atlas's orbit. For decades, scientists had relied on these forces to explain the motion of celestial objects, and they had always worked. Gravity was the primary force, with smaller contributions from solar radiation and outgassing. Outgassing, in particular, had been the go-to explanation for small shifts in a comet's trajectory. When a comet moves through the solar system, gas and dust are often ejected from its surface, creating jets that can nudge the comet off its predicted path. This process had been observed and measured many times, and it was well understood. But when astronomers ran the numbers on 3I Atlas, they found that the usual suspects just didn't add up. For 3I Atlas, something else seemed to be at work, something beyond the reach of gravity and outgassing. The object's orbit was shifting in ways that couldn't be explained by the forces we had come to rely on. The deviations were too subtle to be easily noticed, but they were persistent. As more and more data came in, it became increasingly clear that this was not just an anomaly. This was something that required a new explanation, something that might not fit with our current understanding of the solar system. This presented a major problem for astronomers. They had a set of models and equations that they had used to track the movement of celestial bodies for years, and now those models were being called into question. The standard rules of motion, which had been used to predict the movement of comets, asteroids, and other objects for centuries, were suddenly not enough to explain what was happening with 3I Atlas. If a massive object like 3I Atlas, traveling at an incredible speed, could break the rules of orbital motion, then what else might be out there that we couldn't explain? What other objects were passing through our solar system, behaving in ways that we didn't yet understand? The stakes here were high. This wasn't just a curiosity or a minor puzzle to solve. This was a challenge to the very way we understand the motion of objects in our solar system. It wasn't just about figuring out why 3I Atlas was moving the way it was. It was about understanding what this meant for our broader understanding of the universe. If the current models of comet motion were inadequate, what else were we missing? What other objects might be flying under the radar, moving in ways that we couldn't yet explain? As the analysis of 3I Atlas continued, scientists began to realize that this object was raising more questions than answers. The discovery of 3I Atlas had started as an exciting find, but it quickly turned into a deeper investigation into the limits of our knowledge. Every new observation brought with it more data that didn't quite fit the standard models. The object's motion seemed to be dictated by forces that were not immediately obvious, and this prompted astronomers to dig deeper into the data and re-examine the models that had served them so well for so long. The implications of this were profound. If 3I Atlas was indeed moving in ways that couldn't be explained by the laws of physics we currently understand, then this could mean that there are gaps in our knowledge that we hadn't even considered. Perhaps our understanding of gravity, radiation pressure, or even outgassing wasn't as complete as we thought. The truth is, there are still many unanswered questions when it comes to the movement of objects in space. And 3I Atlas was just the latest reminder that the universe has a way of keeping us on our toes. As we continue to study 3I Atlas and similar objects, it's clear that we're in the midst of a new era of discovery. What was once thought to be well-understood territory is now revealing itself to be much more mysterious than we realized. Every new interstellar object that passes through our solar system offers us a glimpse into the unknown. And with 3I Atlas, we may just be scratching the surface of a much larger mystery, one that could reshape our understanding of the cosmos. What makes 3I Atlas particularly intriguing is that it's not the first interstellar object to present these kinds of challenges. In 2017, astronomers observed a similar phenomenon with another interstellar object, Oumuamua. Like 3I Atlas, Oumuamua's path seemed to be shifting in ways that couldn't be explained by gravity alone. The similarities between the two objects are striking, but what makes 3I Atlas so much more significant is its sheer size and mass. It's orders of magnitude larger than Oumuamua, which makes the unexplained deviations in its path even more puzzling. The strange behavior of 3I Atlas, which had already drawn attention due to its unprecedented speed and trajectory, now became even more puzzling as scientists delved deeper into understanding its motion. As is typical for most objects passing through the solar system, their movement is primarily influenced by two key factors: gravity and outgassing. Gravity, of course, is the primary force that governs the orbits of most celestial bodies, from the planets to the smallest asteroids. But outgassing, or the release of gas and dust from a comet's surface, can also play a significant role, nudging the object off its predicted path. Outgassing is often seen as a secondary effect, but it has been well studied and understood by astronomers. So when 3I Atlas began to behave in ways that couldn't be explained by either gravity or outgassing, the mystery grew deeper. Outgassing occurs when a comet approaches the sun. The heat from the sun causes the ice trapped in the comet's nucleus to vaporize, and as the gas escapes, it carries dust particles with it. These jets of gas and dust act like tiny thrusters, pushing the comet slightly off its original course. This process is somewhat like a balloon releasing air. The escaping gas causes the object to move in the opposite direction. For most comets, this is a predictable and measurable effect, and astronomers have used this principle to accurately predict the motion of numerous objects in the past. For decades, scientists have understood how the amount of gas released and the speed at which it escapes can shift a comet's trajectory. Take the example of the Rosetta mission to Comet 67P Churyumov-Gerasimenko, which provided us with a detailed look at how outgassing works. The Rosetta spacecraft observed the comet closely, tracking how its surface released gas and jets that not only altered the comet's trajectory, but also caused its rotation to speed up or slow down, depending on which jets were active. In some cases, the outgassing could even cause the entire nucleus of the comet to spin. This showed just how powerful outgassing could be in influencing a comet's path. In fact, orbital models today must factor in the effects of outgassing to make accurate predictions about the movement of comets. Without this adjustment, predictions would quickly go off track. For most comets, the relationship between mass and outgassing is straightforward. A smaller comet with less mass will be more easily affected by the force generated by outgassing, while a larger, more massive comet will require a much greater force to produce the same amount of drift. This is a key concept when it comes to predicting the motion of these objects. The more gas a comet releases and the faster it escapes, the greater the shift in the object's orbit. But for 3I Atlas, this principle didn't seem to apply. While 3I Atlas was massive compared to typical comets, estimates placing its diameter between 3 and 7 meters, this alone didn't account for the deviation in its orbit. Its size was significant enough that the gas released from its surface should have been relatively insignificant in changing its course. For a comet of this mass, the outgassing would not have produced enough force to cause the observed shifts in its trajectory. The usual model, which incorporates both gravity and outgassing, didn't seem to match the data for 3I Atlas. In other words, the object was behaving in a way that couldn't be fully explained by the forces that we know influence most comets. It was becoming increasingly clear that 3I Atlas was a unique case, one that didn't follow the usual rules. If gravity and outgassing weren't enough to explain the object's erratic motion, then what other forces were at play? This question became the focus of many astronomers as they examined the data more closely. As they began to run simulations and refine their models, they found that the residuals, the small differences between where 3I Atlas was predicted to be and where it actually was, began to shift. These small discrepancies didn't add up, and no amount of tweaking the standard models could close the gap. Each new observation showed that the object was veering slightly off its expected path, in a way that couldn't be explained by any of the known forces. For astronomers, this was a serious issue. If the standard models were failing to predict the movement of such a large object, it raised questions about what other objects in the solar system, both known and unknown, might be following unexpected paths. What else could we be missing? What other mysteries lay hidden, their movements unaccounted for because our models were incomplete? The potential consequences of this were huge. If the standard explanations of orbital dynamics were no longer sufficient, what did that mean for the future of space exploration and our understanding of the solar system? In their attempts to reconcile these discrepancies, astronomers considered various possibilities. One potential explanation was that 3I Atlas's surface might have been unusually porous or loose, with a structure more like a rubble pile than a solid mass. If the object was less dense than expected, it might have been more susceptible to the forces of outgassing. However, the data from the object's coma, the halo of gas and dust surrounding it, didn't support this theory. If 3I Atlas was a loose rubble pile, it would likely show signs of fragmentation, but this didn't appear to be the case. There were no indications of major structural changes, and the object's surface seemed stable. Another theory put forward was that the object's nucleus could have fractured in a way that shifted its center of mass, which might explain the observed changes in its trajectory. However, no evidence of such fragmentation had been detected. The data didn't support this hypothesis either. As astronomers continued to investigate, they were faced with a frustrating realization. The forces that typically shape the path of an object like 3I Atlas, gravity and outgassing, didn't appear to be sufficient in this case. Something else was at play. This situation led to a deeper examination of the physical and chemical properties of 3I Atlas. One of the first clues that something was amiss came from the James Webb Space Telescope, which observed the chemical makeup of the object's coma. What the telescope found was extraordinary. For every molecule of water vapor in the coma, there were 8 molecules of carbon dioxide. This was highly unusual, as most comets in the solar system are predominantly water-based, with carbon dioxide playing a secondary role. But in the case of 3I Atlas, carbon dioxide was the dominant gas being released. The quantity of carbon dioxide was staggering, with the object expelling gas at a rate of 129 kilograms per second. This dwarfed the 6.6 kilograms per second of water vapor being emitted. The question now became, why was this object releasing so much carbon dioxide, and what effect was it having on its trajectory? The answer, it seemed, was that even though there was a large amount of gas being ejected, it wasn't having the desired effect on the object's motion. Despite the large amount of gas being released, the calculated force from the outgassing still wasn't enough to explain the observed shift in the object's orbit. At the same time, further observations from the Very Large Telescope added another layer of mystery. Spectroscopy revealed 22 distinct emission lines from atomic nickel, with no traces of iron. This was another anomaly. Normally, nickel and iron are found together in cosmic objects, especially in meteorites and objects that have been formed in supernova explosions. The absence of iron was highly unusual and suggested that the nickel in 3I Atlas's coma was coming from a process that was not typical for most comets. It was possible that exotic processes were at work here, but the exact mechanism was still unclear. All of this data pointed to the same conclusion. 3I Atlas was not following the expected rules. Its outgassing, though significant, wasn't enough to explain its orbital deviations. The chemical makeup of the object's coma was unusual, and the presence of nickel without iron suggested that something extraordinary was happening. But no one knew what that something was. It was becoming increasingly clear that 3I Atlas was not just another comet. It was a cosmic anomaly, one that was defying the laws of motion that had governed the study of comets for centuries. As astronomers continued to investigate 3I Atlas, the mystery deepened, and the object's odd behavior pushed the boundaries of our understanding even further. Each new observation seemed to reveal more questions than answers. Theories that had worked for centuries in explaining the motion of comets and asteroids were suddenly proving inadequate, and the data that came in from various space telescopes only added layers of complexity to the puzzle. As scientists pored over the findings, they were confronted with a fundamental truth. The forces responsible for 3I Atlas's movement were not entirely understood. Gas jets, which had been the go-to explanation for slight orbital shifts in other comets, were simply not powerful enough to explain the observed changes in the trajectory of this object. Gravity alone wasn't sufficient either. So, what was responsible for the strange behavior of 3I Atlas? One of the most compelling clues came from the data collected by the James Webb Space Telescope. The chemical composition of the object's coma, the cloud of gas and dust surrounding it, was unlike anything scientists had ever seen. Most comets in the solar system are composed predominantly of water ice, with small amounts of carbon dioxide and other gases. But 3I Atlas was different. For every molecule of water vapor in its coma, there were 8 molecules of carbon dioxide. This was an extraordinary ratio, far higher than what is typically observed in comets. In most cases, carbon dioxide plays a supporting role, but in 3I Atlas, it appeared to be the dominant component. This raised several questions. Why was there so much carbon dioxide, and what effect was it having on the object's motion? The sheer quantity of carbon dioxide being released by 3I Atlas was remarkable. The object was expelling gas at a rate of 129 kilograms per second, far exceeding the 6.6 kilograms per second of water vapor being emitted. The large amount of gas released would typically be expected to generate a significant force, enough to slightly nudge the object off its predicted path. But in this case, the force generated by the outgassing still wasn't sufficient to explain the deviation in the object's orbit. Even with such a large amount of gas being ejected, it wasn't moving the needle far enough to account for the observed orbital shift. This suggested that there was another force at work, one that was not being captured by the traditional models of comet motion. Despite decades of research into the effects of outgassing, 3I Atlas had shown that the standard models were incomplete. The force generated by gas jets on comets, although well understood, simply wasn't powerful enough to explain the movement of this massive interstellar object. The discrepancies between predicted and observed positions of 3I Atlas were too large to be accounted for by the usual suspects. Something else was pushing the object, but no one knew what it was. The chemical makeup of the coma, the unusual carbon dioxide to water ratio, and the presence of nickel without iron only added to the mystery. These peculiarities were unlike anything seen in other comets, and they suggested that 3I Atlas was not a typical comet at all. As astronomers continued to explore different theories, they considered the possibility that the object's mass and structure were influencing its movement in unexpected ways. One hypothesis was that the object might have a much lower density than expected, perhaps a loose rubble pile rather than a solid mass. If this were the case, it might be more susceptible to the effects of outgassing. However, this theory didn't hold up under scrutiny. The data didn't show the kinds of structural irregularities that would be expected if 3I Atlas were a loose conglomerate of materials. Furthermore, the chemical composition of the coma didn't support this idea either. If the object were made up of loose, porous materials, it would likely exhibit signs of fragmentation, but no such evidence had been found. Another potential explanation was that 3I Atlas might have undergone some kind of fragmentation event that shifted its center of mass. This could have caused a slight change in the object's orbit. But again, the data didn't support this theory. There was no evidence of any major breakup or disruption in the object's structure. The object seemed stable, with no signs of the kind of violent event that would be required to cause a shift in its center of mass. As astronomers considered these possibilities and ran more simulations, they found that none of the traditional explanations were sufficient to explain the object's movement. Theories about fragmentation, low density, and even outgassing were tested and found wanting. But one thing became clear: the object's motion was not being driven by any of the known forces we typically rely on to explain the movement of comets. The forces at work here were something new, something we didn't fully understand. With every explanation that failed to account for the object's behavior, astronomers began to entertain more radical ideas. One such theory was that 3I Atlas might be powered by an exotic form of propulsion, something unlike anything we've seen before in the natural world. Some scientists began to speculate that the object could be a type of solar sail, a thin, ultralight sail that uses the pressure of sunlight to propel it through space. Solar sails are a real technology, used by spacecraft like the Japanese Ikaros mission, but these sails are usually lightweight and relatively small. Could it be possible that 3I Atlas was a natural object with a similar property? A large, thin surface that was catching sunlight and using it to accelerate. This idea was purely speculative, but it was one that some scientists were willing to entertain. Harvard astrophysicist Avi Loeb was one of the prominent voices suggesting that 3I Atlas might be an artificial object, designed with a structure that could take advantage of sunlight in a way that no natural object could. He proposed that the object could be a giant solar sail, designed to capture and utilize solar radiation to propel itself through space. The idea was a bold one, and it attracted attention from the scientific community, though it was met with skepticism. While there was no direct evidence to support the notion that 3I Atlas was artificial, the very fact that such a theory was being considered highlighted just how unusual the object was. If gas jets and gravitational forces couldn't explain the observed motion, could it be possible that the object was engineered in a way that defied the laws of physics as we understand them? For most astronomers, the idea of 3I Atlas being artificial was a step too far. But the fact that this theory was being discussed at all underscored the extraordinary nature of the object. It wasn't just that 3I Atlas was moving in unexpected ways. It was that all the usual explanations were failing. Whatever was driving this object's motion, it was something new, something that scientists had not anticipated. And that left astronomers with an uncomfortable realization. The models they had been using to track and predict the movement of celestial objects were incomplete. As astronomers continued to investigate 3I Atlas, they found themselves grappling with a growing sense of uncertainty. If the laws of physics could not fully explain the object's behavior, then what did that mean for the future of space exploration and our understanding of the cosmos? If 3I Atlas was truly an anomaly, what other objects out there might also be defying the rules of orbital mechanics? What else could we be missing? These questions raised the stakes for astronomers and highlighted the need for new models and theories to better understand the motion of interstellar objects. One thing was clear: the mystery of 3I Atlas was far from over. As the data continued to pour in and new observations were made, astronomers remained focused on uncovering the truth behind the object's strange behavior. But the question remained: what force, natural or otherwise, was at work here? Until that question could be answered, the mystery of 3I Atlas would continue to challenge our understanding of the universe. Looking ahead, astronomers are already preparing for the next phase in the study of interstellar objects. The Vera C. Rubin Observatory, with its advanced capabilities and long-term survey of space, is set to revolutionize our ability to detect and track interstellar visitors. With this new technology, astronomers expect to detect dozens of interstellar objects each year, providing more opportunities to study objects like 3I Atlas and uncover the secrets of the forces that shape their motion. The discovery of 3I Atlas is not just a curiosity, it is the beginning of a new era in our understanding of the universe. And as we continue to explore the cosmos, the search for answers to the mysteries of interstellar objects will push the boundaries of science and our understanding of the natural world.